New day, new room. Looney Tunables. CVE 2023-4911. That's all, sec folks. So let me see. CVE identifier has been assigned to Qualys Threat Research Unit (TRU) in October 2023 due to critical security flaw in GNU C Library dynamic loader, known as LDSO. This vulnerability poses significant risk since it allows escalating privileges of logged-on user and obtaining full control of vulnerable instance. This vulnerability was introduced in GLIBC version 2.34 through commit to ED 18C. The vulnerability affects recent version of major Linux distributions such as AHL, Ubuntu, Fedora, Debian, Amazon Linux, GNU, and other distributions that uses GLIBC to deploy. I don't need it. Let me see Qualys Threat Research and their blog. So we have privilege Looney Tunable, and we can see glib Tunable. This is where they got the name. Environment variable. We have successfully identified privilege escalations. We have Fedora 37 and 38, Ubuntu 22.4 and 23.4, Debian 12 and 30, the most recent ones. So let me see what were they. So we have a system base. I've got this machine up and running. Let me see. LDSO, dynamic linker loader. Whenever you execute the ELF file that depends on shared library ISO files, the operating system will need to load such libraries and link them to your executable so that any shared functions are available to your program during its execution. In Linux systems, this is normally managed by LDSO, an executable pre-packaged as part of the GLIBC library. Every ELF executable contains a section named interrupt.interrupt where the location of its required loader is specified so that the operating system knows which loader to use. For most ELF files in Linux, it is LDSO, probably with significant slight different name. To check the .interrupt section of the ELF file, you can use following command. Let me real quick check this one. Read ELF user bin man p inter p. Okay. LDD user bin man. Okay. We can also check libraries are needed to run man command by using LDD. Let me real quick check what's LDD. Print shared object dependencies. Here we can see that the name man command depends on libzso1, and we can see Where can we find this one? Usually the required libraries are searched in specific set of locations in the system, including default lib directory. You can read. Let me read this one. LD documentation, dynamic linker, so can be run inherited by some dynamic link library shared program find load prepare for lib5 using directories default paths lib user lib on some 64-bit architectures default path shared objects lib64 or user lib64. Okay, so we have dynamic string tokens, LD library pass, LD preload, LD audit, and so on. Let me see what variables we have. Lib platform. Okay, using LDT, this one. DTR pass. DTR pass to influence the library search path. When compiling the program, you can specify additional paths where you want LDSO to look for libraries. Those directories will be embedded in your program's ELF file and passed and used by LDSO when loading executables. This allows you to override the default library search path and have your program search in an alternative location first. For example, you could compile a program with following options to that end. We can see here our path is set to be temp. Whenever LDSO loads your executable, it will first check temp for libraries, then default regular library search path. Let me check this one real quick. I will take hello world C program. Let me real quick copy this one. Nope. Let me copy this one now. Nope. Okay, dear. Looney. Now. Export C. Let me see. Okay. So now we can GCC WL enable new D tags WL R path TMP oh my app exploit C. Let me see. LDD my app. Okay, nothing special, but I can now modify the G behavior via GLIBC tunables. So, to better understand how this vulnerability works, let's have a look at how the dynamic library LD so briefly works. Once it gets executed, it checks specific environment variable called GLIBC tunables. Those features, aka tunables, allow developers to dynamically alter the runtime library behavior. One example to understand how this process works is the following. So we can set malloc check1 malloc the hash max. The variable sets maximum size chunk that may be stored in the cache. Let me print this G. We don't have this one. Okay. Click continue learn. Let me see. In line 282. Tunable is name. Tunables. Okay. The code looks for any variable with the name glibc tunables in the environment variable. Let me real quick SSH to this machine. No priv 10 info. Yes, password 321. Okay, let me echo G. We don't have this one. Okay, so looks for any variable with this name in the environment variable envp and copy them into the new envp like this. Next method, pass tunable. New length +1 valve. env valve is null. Process sanitize. Ensure settings glibc won't result in any problems or vulnerabilities. The process copy new env to priv is substituted for the original. Where do we have this one? New is substituted for the original glibc tunable. Okay. Inside pass tunable, we have pass tunable. Okay. Inside pass tunable, the code examine the copied glibc tunables to break it down into individual values. So if gtunable looks like this, then there is pathing element breaking with divided by column, so we can see in here breaking with, we didn't find name value pair before encountering the column. That's it. So this, all this is doing is breaking this variable value elements. To break it down into individual name value pairs, it does this by searching for equal sign and colon in a copy data. Here where it gets interesting. The code is careful about security. It removes dangerous tunables, specifically those marked as SXID array. Those security-related tunables instruct GLIBC modify security attributes or permissions for a process. Those attributes could include changing evaluated privileges typically associated with set user ID or set group ID. The vulnerability occurs when GLIBC tunables contain unexpected input, like tunable A. In this case, instead of gracefully handling it, code copies the entire input as if it were a valid setting. This issue occurs when the tunable R of SXID ignore, which should not be removed during the first iteration of the loop. The entire tunable A is copied to the tune string, filling up. Later, at lines 248, 247, 247, searching for pointer, found, searching for line break or something. No. As a result, P still points to the value of tunable 2. During the second iteration, tunable 2 is incorrectly appended to tunable string, causing buffer overflow because it is already full. Okay. I can't say that I understood it. For the first time, so we have string tunable 1, tunable 2, AA is copied to the tunable string, filling it up. Later at the go fails to increment the pointer P because no colon was found. As a result, P still points to the value of. During the second iteration, so we have if P lang don't increment P. Okay. It couldn't increment it. So we start. Where do we use P? P, okay. So while P lang and P not length plus. So here length just finished this for loop and proceeded to this P len, but we cannot find the columns. Len. Okay. Let me see how it works. This section will dig more into exploitation POC. Oh, we have POC for this one. Let me see POC. This POC, aka exploding bug, loader, environment passing. Okay. Let me see how it is done. That's it. bit array set shellcraft set UID to 0, set GID to 0 plus SH. Okay, ISM read lib start main defined open the write this one, all this, write all this jazz into the dx defined. Okay. I want to see it playing. No. Just open the file. And let me play this one. I don't want to open it, but read D. I'm not sure, but let me play with this one. Move. Move 10 libc. GLIBC in here, and GLIBC by done. Let me see. Okay. I get this amount of data can crush anything. So the exploit creates different arrays. Line 41. What? Line 41? We have 14 lines in here. What do you mean? Maybe like 40? Environment variable triggered buffer overflow. GC when program is executed. This variable is created too. We are looking into different. Okay. Now here we go. Here we have line 41. Different arrays. And here we have filler. This one was created to pare away the loaders read-write section. It filled with long sequence of F characters, KV. This variable is the payload that will trigger the buffer overflow. It filled with long sequence of A characters. Filler to similar. Part away any extra portion. It is also filled with sequence of F character. DTR path. This variable is used to craft specific value to overwrite memory region in the exploitation process. This will be 47. This 43, 53, 47, 53. Okay. Weaponization, the payload in does follow two else. It overrides a segment of the stack with the index pointing to string. With qual as a content. The intention here is to manipulate the stack so that index points to the specific memory address where character double quote is stored. The stack is a region of the memory used for storing local variables and function call information during program execution to add exploits complexity. Modern operating system randomize the stack location, making it difficult to predict where index will end up in memory. Exploitation. The exploit uses trial and error approach to account the randomness of the stack's location. It repeatedly runs the program, forking and executing it until it gets lucky and fixed addresses matches to the addresses where stop index points to double quote. This effectively manipulates the library search path to point the directory named double quote, which will contain the malicious version of libc 6. So, process for generating forged libc so consists of copying libc 6 but replacing with libc star main function with custom shellcode that does suite set uid 0, set gid 0, exec bin bash sh. You can find Python script for these here. Let me see this one also. It is the same one. Okay. The program enters to the loop where for child in the child process it attempts to execute user bin su help. If child process takes longer than 1 second, it assumes that it is returning from the shell, indicating the potential successful exploit. Let me run all these jars at the system that was dedicated to it. Let me see. We have gen. We have all we need in here. Okay, try it yourself. Now it's time to practice vulnerability deploy machine attach. Try. Let me see what are my password 3. User may not run sudo on Looney Tunes. Okay. First execute. Let me execute this one. GLIBC. Never to disable functionality. Brief. Update to never. Okay. Do I need to do it now? Checking new version of do. Disable functionality never all the way. Or add. I don't understand. What are you? No. config. Nope. etc. Config. Okay. Let me copy this one. Another shot. Okay, how is this working? What do we have here? libc SEO 6. Very nice. So now GCC L EXP we can EXP ID. Alright. Okay. Let me cut the root. That's it, secure, folks. Okay. In this one, we have analyzed the complexity of exploiting buffer overflow in GNU C Library by messing with the loader LDSO and its environment variables. By abusing this vulnerability, an attacker can quickly escalate this privilege, becoming root in the target system. For this reason, all Linux vulnerability systems should be patched and updated for the latest version of GLIBC. You can check fixed version issued for every distribution representative security advice repositories. So we have everything we need in here. Remember that similar strategies may be also applied to other system libraries, highlighting the importance of preventive security measures in security and cybersecurity. That's it. Let me close this one. So, bye bye. We out.